All right, it's time for class. So we just start, and we have six here. There were nine in the group, but seems some of you are difficult because it's very. Well, actually, it's midnight for some of you. I would ask you to try to find some suitable time. This is a difficult time actually, not for just one, for everybody at this time. So we need to make some sacrifice to make our group to work better. All right. I know for some of you, yes, you will be if we adjust the timetable, it will cause some trouble to you. But if the trouble is not that big, and the trouble for the other people is so big, um, I think if we make some sacrifice to make some adjustment, it is suitable because here we are a group, and I would mention this that when actually at any time of our life, um, to have a mind that we should work as a group is important. And later on, when you go to work, you always work as a group, and as a team, every member should cooperate. So this means sometimes, yes, you have to sacrifice something of yourself to for the sake of the whole team. All right. So I hope you can work out a suitable time to make this course easier for, or will have a better teaching effect. Okay. All right. We'll just start. For the chapter 2, we are going to introduce the modeling of a dynamic system. This is the first step for the control system design. Well, in this chapter, we will have mainly 4 sections. The first section will be the review of Laplace transform. I don't know if you have learned this before. Actually, it's a mathematics branch. It, it's a mathematical tool, a very powerful tool. It's very useful in the control system design. So we'll take some time to go over the Laplace transform. We'll introduce the basic contents, the definition, a typical a phone calls many times. Well, a very annoying call from a garage. Very strange. All right. In this section, we are going to introduce the basic definitions, the typical transform of some time domain functions, and the usage of Laplace transform in solving the ordinary differential equations. Okay, that's the in section 2.1. Normally in this university for bachelor students, we may take about 16 hours total to introduce this part. But here it's just a brief, maybe just 1 hour or two when we finish this part. And for some more contents, you may refer to some reference book, textbooks. Okay, and this is this part, the first part. Then the second part, we're going to introduce the transfer function model. And this is the way that the classical control theory to model the system. All the theories for classical control will be based on transfer function. So for the analysis, for the controller design, all just based on the transfer function. And the third section is the state space model. This is for the modern control theory. It's based on the matrix theory. But matrix is not that difficult, so we will not go over through the theories of matrix. So we will mention that when we meet them. Okay. And the fourth one is the conversion between transfer function TF. That's the first letter of the two words, the transfer function TF, and the SS state space model. We can convert from TF to SS, and then we can convert from SS to TF. Well, that's going to be the main content of this chapter. Okay. All right. We go through the first one, the review of Laplace transform. But first thing is the definition of Laplace transform. Well, if a time domain function xt satisfies two conditions. First, when t is smaller than 0, all the x will be 0. When t is greater than 0, then xt is piecewise continuous in each finite interval. This is the first requirement for the xt. Well, this is not difficult to satisfy, but the second one will require that the integration of xt times exponential minus st from 0 to infinite, this integration exists. And s is a complex number, complex variable, the u plus jv, where j is the imaginary unit. Well, I guess you all know the complex analysis, right? You know the complex number, right? Okay. Well, actually, j means the square root of minus 1. Normally, in real analysis, square root of minus 1 is meaningless. We don't have that number. But in complex analysis, we have this unit as a square root of minus 1. So s is a complex number. It has a real part u and an imaginary part v. Okay. This integration exists for suitable s. Then we say the xt satisfy the two conditions. Then we define the Laplace transform of xt just as the integration. So the integration, if the integration exists, then the integration is the Laplace transform of the xt. So originally, this xt is the function of a time t. But after this integration, the t vanishes because we do the integration of t from 0 to infinite. So t vanishes, disappeared. after this integration. After this integration, the variable has become s. So now s is the variable, where and s is a complex number. So that's the change. So we change a time domain function to a complex function. This is Laplace transform. All right, we use a, well, normally when we talk about the time domain function, we use a lowercase letter. When we talk about the Laplace transform, the complex function, we use a uppercase letter. All right, so xt to be the primitive function and f to be the imagined function. Well, for each different xt, we will have different f. So the 1 to 1. All right, we're now going to look at some special typical time domain functions, which are very useful in the analysis and the controller synthesis of a control system. The first one is a unit step function. This function equals to 1 when t is greater than 0. Oh, sorry, this symbol is wrong. Should be greater, no less than 0. And to be 0 when t is smaller than 0. Sorry for the mistake. Okay, I will correct it after class. Well, this is its time domain. And if we look at the figure, well, the function is like this. When t is smaller than 0, it's just 0. The function itself is 0. And when t is greater than 0, it is 1. So it's just like the function goes up a step at the time t equals 0. It jumps up and keeps constant. So the shape looks like a step. So we call it a step function. Well, this one is very useful when we test the system's dynamics. We always, well, quite a lot of cases where we use this signal to stimulate the system, and we watch the system's response. Okay, so we'll see what is the Laplace transform of this function. So we do the integration according to the definition. We time this time domain function 1t with exponential of minus st, and we do the integration. Well, actually, because 1 we integrate from 0 to infinite, so we will not well, in this case this time domain function is just 1, just unit. So actually the integration is just to integrate the function exponential function, exponential of minus st, just to integrate this one. Well, this is easy to go. We take down a minus s and put it in the denominator, and we'll put this exponential function here. Well, the minus 1 over s times exponential minus st is the integration. And we substitute the upper bound infinite and the lower bound 0 into this equation, into this integration. We will get the result. Okay, so we put the infinite into this equation. How much is the value? So it is here. It is exponential of minus s times infinite. Because s is a finite variable, in order to make this integration meaningful, we need this value to be a limited value. Well, as the t is infinite, when this exponential function will be 0 or infinite, depends on the choice of s. For example, if we choose s to be 1, then this exponential, it is exponential of minus infinite, then this integration, the number is going to be 0. But if we choose s to be minus 1, here this integration is going to be exponential of plus infinite. Then it is going to be positive infinite. When this integration, we will say this integration doesn't exist because the number is not a finite number. So here we will choose s to make this number a finite one, and we can find such s. So this we can find a suitable s to make this number a finite one. So this integration exists. And in this case, when we substitute the upper bound into this integration, it is 0. Okay, it is 0. Then we substitute the lower bound into this integration. It is exponential of minus 0. So for the integration, for the exponential function part, when we substitute the lower bound into this equation, it is 1. So the total will be minus 1 over s. And we should know, for the calculation of this integration, we use the value at upper bound, subtract the value at the lower bound. So the upper bound is 0, the lower bound is minus 1 over s. So totally, the result is 1 over s. That's the result. Well, that's the Laplace transform of the unit step function. Okay, well, that's the first one. Well, very commonly used in control system analysis. So I would think I would require you to memorize this. Okay, right. Well, the second one, a unit ramp function t. So here the function is not a constant, it's a slope. It's a slope where this function equals t when t is greater than 0. Okay, again we do it according to the definition. It's the function times exponential of minus st, and then we do the integration from 0 to infinite. Well, we put the exponential function into the d, then we should put a s minus s in the denominator. Well, this one is just a transform for the original integration. Then we can use the formula for the integration. We get this. Well, how do we get this? How do we get this function? It's this function minus t over s times exponential minus st. Here we put it here, and substitute the lower bound and the upper bound, and then we should subtract a integration in which we reverse, we change the position of the two functions. So we take the exponential of minus t out, and we'll put the minus t over s in. Well, then we just take the minus 1 over s out. So we get this result, okay? All right. Then we calculate the first part. When we substitute the upper bound into this equation, this exponential part is going to be 0. Well, minus t over s is going to be infinite, but this one is much smaller. The decrease of exponential minus t is much greater, much faster than the increase of t over s. So totally, when we substitute the upper bound into this equation, we get 0. And if we take the lower bound into this equation, well, because here we have a minus t over s. Since t is 0, then the total is still 0. So the first is just the 0. And we'll do the calculation of the second part. Well, this integration is easy to go because we can take this minus 1 over s totally outside of the integration. And then the inside is just the integration we calculated just now. It's the unit step function. So we get this result, and the final result is 1 over s squared. Okay, that's the unit ramp function. Well, we have mentioned this signal at the first class when we introduced the dynamic error, right? A system is supposed to trace with the slope signal. We have a dynamic error. Well, so this signal is also commonly used, frequently used in the system's performance analysis. Okay, the third one is the power function. With this is not t, it's going to be t squared, t cubic, t's nth order power. Well, we would do the integration just in the same way. We get the result, the 1 over s cubic, 3 over s fourth order, etc. Right. So this is the power function. But we don't, for the higher order function of t, higher order power function of t, we don't very often use them in the analysis, but use just the first two, the step function and the ramp function, unit ramp function. It's very commonly used, very often used. Okay, well, here the fourth one, exponential function, a minus at. Well, when we have a positive a, what's the curve of this equation? It converges, it goes down to 0 to the x-axis, right? It goes down and converges to 0 as t increases. So for this equation, for this time domain function, we will look at its Laplace transform. We will just do it according to the definition. This is the time domain function times exponential of minus st. We do the integration. Well, actually, the production of the two exponential function, we can put the the minus at and minus st together. So here it is exponential of minus s plus at. Well, this integration is not difficult. Again, we take down the s plus a to be the denominator, and again we write down the exponential function itself, and we substitute the upper bound infinite and lower bound 0 to this function. Okay, so similar to the integration of the unit step function, the final result is 1 over s plus a. So we have a time domain function exponential minus at. We have Laplace transform 1 over s plus a. This is also very common, very often used. And if a dynamic system behaves in this way, that it goes down without oscillation, that's very ideal for the stability. So, well, this function, I would suggest you to memorize the relationship between the two. So you should bear in your mind that the Laplace transform of exponential minus at is s plus a, 1 over s plus a. If you are given the Laplace transform of 1 over s plus a, you should know its primitive function is exponential minus at. So this is very important one. This is a very important pair of functions. All right. Well, the sine function f sine omega t. Well, I have introduced in the first class. The sinusoid wave is also often used to evaluate the system's performance, especially when we talk about the rapidness, when we talk about the bandwidth. We often use the sinusoid wave to see at which frequency you can follow the signal, at which frequency you cannot follow. So this is also a very useful function in the system analysis. So we should be familiar with its Laplace transform. Okay, that's the time domain shape. Well, here before we go through its Laplace transform, let's review a Euler formula. Well, if the exponential here is not a real function, if it is an imaginary function, j omega t, exponential of j omega t, it means the cosine omega t plus j times sine omega t. But if it is minus j omega t, exponential of minus j omega t, then it is cosine omega t subtract j sine omega t. So from these two Euler formula, we can work out that sine omega t equals 1 over 2j with exponential of j omega t subtract exponential of minus j omega t. Okay, well, this is the preparation before we start the integration, the Laplace transform. Okay, then the Laplace transform of sine omega t can be written in this way. We put this, we substitute this, we replace s omega t with this function. And we can see here, it's just all about exponential functions. And for the integration of s or exponential function, it is quite easy. We'll just give the result, because here I will put them together. It is s minus j omega t, and here it is minus minus s plus j omega t. So here will be s minus j omega, s plus j omega. We'll do the combination. It's just two fractions, so we put them together. We combine them into one function. Well, it is omega over s squared plus omega squared. So for this integration, we have convert the time domain function sine omega t into a complex function omega over s squared plus omega squared. Okay, this is the sine function. Well, for cosine function, it will be similar. It's s over s squared plus omega squared. Okay. Well, actually, there are lots of time domain functions, very useful, very often to be found in our dynamic systems. So the mathematicians had already worked them out to work out the integrations, and they put them in a table. Here we have a list for some typical Laplace transforms, but the table is more than that, more than this. We have lots of functions, lots, right? And you can find the table on some textbooks, or maybe just online. You can find this, so you can when you meet some different time domain functions, you can go to the table to check the table to see if the function is already there or not. Okay, so here with a Laplace transform, we transfer the time domain function into a complex plane function. The original variable, of the original, the primitive function is t, but the variable for the imaginary function is s. Well, later we will just work on the imaginary function. We will analyze the imaginary function, and we will tell you what's the behavior, what's the characteristic of the primitive function. Okay. Well, this is the Laplace transform for the typical functions. I require you to memorize some of them. Here, the unit step function, this pair, you should be very familiar with this pair. And this pair, exponential function, this pair, you should be very familiar. Okay. All right. The third part of this section, we're going to introduce the basic properties and the theorems of Laplace transform. The first one is its linearity. Well, we have two time domain functions, x1t and x2t. And for x1t, its Laplace transform is x1s. For x2t, its Laplace transform function is x2s. Here we have a new time domain function. It's a linear combination of x1t and x2t. That is a times x1 plus b times x2. It's a linear combination of the two. Then what's the What's the Laplace transform of this new function? Well, we do the integration according to the definition. It's just this time domain function times exponential minus st, and we can get this result. It is a times integration of x1 times e exponential minus xt plus b times integration of x2 times exponential minus st. So actually we can see that it is just a times x1s plus b times x2s. So if the time domain function is a linear combination of two functions, then the Laplace transform is also the same linear combination of the Laplace transform functions. This we call it the characteristic of linearity. Okay, well, the first one. Well, I have some example to some give you one example. Here is a step response step function, but not the unit step function itself. We have a coefficient here 2. So actually it is a times x1t. Here a is 2 and x1 is 1t. And plus x2. No, well, here x2 is a ramp function. So it is a times x1 plus x2. And this Laplace transform will be just 2 plus 2 times the imaginary function of unit step function plus the imaginary function of ramp function. So 2 times 1 over s plus 1 over s squared. That's the Laplace transform of the linear combination function. And the final result will just make the two fractions into a one fraction, that s squared 2s plus 1 over s squared. Okay, right. This is about its first property. But the second one, for differentiation. So here, well, if we have a time domain function xt, and we know its Laplace transform as xs, then what will be the Laplace transform of the derivative of xt? Well, we'll investigate this. Well, we'll do the Laplace transform according to the definition. It's the derivative of x times exponential minus st. We do the integration. Okay, so here, but dt cancelled. So it is integration of my exponential minus st dxt. So we can use the integration formula. Exponential minus st times xt with a upper bound and a lower bound. Then subtract the integration of changing the position of the two functions. And take xt out and put the exponential minus t into the derivative. So we get additional minus s by doing the derivative for the exponential minus st. So we subtract this. Okay. So For the first part, we substitute the infinite into this equation. Well, exponential minus st is 0, and xt is a finite number. So for the upper bound, it's 0. For the lower bound, exponential minus st is unit, and xt is x0. So for the first part, it's just the minus x0. And for the second part, we take the minus s out because it's a constant here. Well, it can vary when we have finally the imaginary function. But here in the integration variable is t, not s. So s is can be regarded as a constant here in the integration. So we take the minus s out, the minus, so we get positive, just a positive s outside. And inside, it is xt exponential minus st. Well, actually, the integration is just the Laplace transform of xt. So we get the result. It is s times xs subtract x0. So we can see here, if we have the Laplace transform of xt, we can easily get the Laplace transform of xt's derivative. It is sxs minus x0 here. Right. We can also do this to higher order derivatives. Say here, the second order. Well, second order, we just use this formula. We use because we have already got the Laplace transform of dx over dt, the first order derivative. So it's again a second time to do the derivative again. Okay, so here it is s times the Laplace transform of the first order derivative of xt, and subtract the initial condition of the derivative function, that is x first order x0, the value when t is 0 of the first order derivative. And we substitute the first result into here, we get this. It's s squared xs subtract s x0 subtract x dot 0. That's the result. So we can see here, for the higher order derivative, we can also get the Laplace transform by the original function's Laplace transform. Okay. And for later on, we will discuss about this. When we talk about control system, in many cases, we will just talk about the relationship, the dynamic behavior under the condition where the initial conditions are 0. Later on, we will explain this. So the initial conditions here, x0 to be 0, x dot 0 to be 0. In this case, the relationship between the Laplace transform of different orders of derivatives and the Laplace transform of the original function is much simpler. Well, it's just like this. For the first order derivative, we time s. For the second order derivatives, we time s squared. For nth order derivatives, we times s nth order. Well, these equations are true when all the initial conditions are 0. Okay, well, this is important. And when we do the transfer function derivation, when we derive the transfer function, we need to use this property as well as the linear property. Okay. Well, here we have a higher order differential equations here. Well, xi is regarded as an input, as a known function, a given function. Xo is an unknown function. This is a ordinary differential equation, a high order ordinary differential equation. And we here want to work out the xo, the Laplace transform of xo under 0 initial conditions. So the initial condition of xi, the initial condition of xo are all zeros. Okay, so we can see how do we do it. All right. So here we do the Laplace transform for each side. Then by the linear property and the differential equation, the relationships, we can see that here for the left side, it is as square xo, bs xo, and c xo. For the left side, the Laplace transform is a linear combination of the three. And for the derivative, it's just s squared times the original one. S times the original one. So for the left side, the final result is as squared plus bs plus c times xo. And for the right hand side, it's again a linear combination. So m times Laplace transform of this one, and n times Laplace transform of this one. And again, we use the differential property. We have ms xi plus n xi. So the final result of the right hand side is ms plus n times xi. So here we can get the final result that xo equals ms plus n over as squared plus bs plus c times xi. That's the Laplace transform of xo. Well, here we use the linear property and the differential property. Okay. Well, that's for this example. All right, we have a break for 5 minutes. Okay. All right. Well, we'll continue. We're going to introduce some other properties. The third one is integration, still under zero initial conditions. Well, we will not go through the detailed derivation of this property. It's just the reverse of the differentiation. Okay, it's just a reverse of the differentiation. So it was s x there. So here it is 1 over s. It's a reciprocal. It's a reverse of the differentiation relationships. Okay. So here it is. If the original function xt has a Laplace transform of xs, then the integration, the Laplace transform of its integration is xs times 1 over s. So here, just the reverse. Okay, and a shift in time. Well, we also do not want to go to the details of the derivation of this property. This happens when in the control system, when we decide a control signal, we need some time to transfer this signal to the actuator. And for the actuator, sometime inside the plant, there also will be some delay. So here we have a delay, and the delay time is tau. So the original one is xs, then the delayed signal, the imaginary function for the delayed signal will be exponential minus tau s times xs. Okay, this is not very often used in linear system theory because this pure delay is more like a nonlinear. Is a nonlinear one. Okay, right. The fifth one, final value theorem. Well, if we have a imaginary function xs, how do we judge the final value of xt without solving out the function of xt? This theorem would tell us how to do that. Well, here the final value of xt, that is the xt when t approaches infinite, equals to s approaches 0 of the function s times xs. So if we want to calculate the final value of xt, we do not need to solve out xt. We do not need to solve out the time domain function. We just time xs with s, and we put the s to 0. We do a algebraic calculation. We can know the final result, final value of xt. Well, here is the derivation. Well, the Laplace transform of the derivation equals to sxs subtract x0. And here, when s equals 0, for this integration, it is x equals 0, sxs subtract x0. Okay. Well, this is just the differential property, and for the differentiation property, we do the limitation when s approaches 0. So here, for this part, when s approaches 0, well, this exponential function is going to be what? This exponential function is going to be 1. So for the left-hand side, the integration, when we put the limitation process inside the integration, we change the sequence. Well, here it is, we do the integration first, when we do the limitation second. When we do the integration, we do the limitation first, then we do the integration. Okay, we change the order, change the sequence. The result will just be the same. All right, so here we do the limitation first. Here will be 1. Then the integration will be just to integrate dxt from 0 to infinite. So integration of dxt is just xt. And we substitute the infinite, the upper bound infinite, and the lower bound 0. We get this result. So it is xt subtract x0. That's for the left-hand side. For the right-hand side, it was just the same. Okay, so we can see here, for both sides, we have x0 cancelled. So finally, we have the result that for xt, when t approaches limit infinite, equals to s approaches 0 for the function of s times xs. Okay. Well, this is the final value theorem. It provides us a easy way to evaluate the final value, especially, well, this final value is useful when we talk about the static response of a system. If we put a unit step to the system, then finally the response of the system will come the static value. And we want to know how much is the static value. And by this theorem, we can easily work the final value out. Okay. Right. Well, the fourth one we are going to, well, that's the properties and the theorems of Laplace transform. And the fourth one we're going to talk about the inverse Laplace transform. Well, for xt, if its imaginary function is xs, and its reverse will be xt. Well, normally for the inverse Laplace transform, we use the partial fraction decomposition. Well, here, suppose we have xs. It is a complicated function with a high order polynomial as numerator and a high order polynomial as denominator. This is the xs. Well, we can do it by the definition to do the integration of this function, but we can see that the integration can be very difficult. Here we provide a different way. We decompose the original function into the sum of some simple functions. So xs we divide it into x1, x2, and xn, and here each function is a simple one. And for xt, it's the sum of the inverse Laplace transform of these simple functions. So this will be easier. We just do the decomposition, and we will just check the table, or sometimes just in our mind we can memorize them. We know it's inverse Laplace transform. Okay. Well, we introduce the detailed process under a simple condition. That is, all the poles are different from each other. What are the poles? Poles are here. We can see here we have a denominator. And if we make the polynomial of the denominator equals to 0, we have an equation. And we can solve out for this equation. We have n roots. We call this as poles. We call these roots as poles. The roots for the denominator, we call them poles. The roots for the numerator, we call them zeros. So here, the poles are supposed to be different from each other. Okay, that's the condition that we can use the method we introduced the following. Right, so here the denominator can be separated into the production of a first order polynomial with here s plus p1, s plus p2 till s plus pn. And the poles will be just minus p1 minus p2 till minus pn. Those are the poles. And the p1, p2, and pn are different from each other. You cannot find the two of them equal to each other. Okay, so and here then we can divide this original function into the sum of the simple functions. Each are just the first order. For the denominator, just the first order, not high order one, just first order. And each has a constant as its numerator. So if we have different poles, the poles are all different from each other, we can divide the original function into the sum of these basic functions. As all the AIs are constant, actually we should have known that the Laplace transform of these basic functions. Well, what are they? Well, I ask you to memorize some important pairs of primitive function and imaginary function. So actually this is the primitive function is exponential minus pit times ai. Well, this is a linear according to the linear property, right? Okay, well here so the first step is to find out the poles, and the second step we have to determine how much these AIs are. How much is A1? How much is A2? How much is AN? Well, there is a residual theorem to calculate this. How to calculate this? We times xs with s plus pk. We time this function with s plus pk. And we replace s with sp minus pk. We can calculate a number. We can work out a value. That is ak, the coefficient here. So if it's p1, we times p1, we times xs with s plus p1. And we replace the functions, all the s there, with minus p1. we can work out a value. Then the value is A1. Okay. Well, this is true for this condition, that all the poles are different from each other. Okay. Right. So the Laplace inverse Laplace transform of xs, actually that is xt, will be the sum of the Laplace transform of each the basic element, and it will be just ai times exponential of minus pit. The I is from 1 to n. Well, this provides us a new way, an easy way to work out the time domain function. Well, it is very useful, and we will use this when later on in the analysis of a dynamic system. We will use this method to work out the time domain response of a dynamic system. Okay, right. We will give you an example. Here we have a function here, xs as s plus 3 as numerator, s squared plus 3s plus 2 as denominator. Well, we can see here, for the denominator, it has two poles. It is -1 and -2. So we can rewrite this function in this way. That is s plus 3 over s plus 1 times s plus 2. So we can divide this original function into two basic parts. That is s plus 1 and s plus a1 over s plus 1 minus, sorry, it should be plus here. A mistake, all right? It should be plus here. Plus a2 minus a2 over s plus 2. And we need to work out how much the a1 is and a2 is. Okay, so a1, it is xs times s plus 1, the denominator here, times the s plus 1. And we substitute s with -1 into the function. So sorry, again another mistake. Here, with xs times s plus 1, what do we get? It is s plus 3 over s plus 2. Sorry, here another mistake. It should be s plus 2, okay? S plus 2. And we have this function. Then we replace all the s with -1. So it is going to be -1 plus 3 as numerator, and -1 plus 2 as denominator. And we get the result as it is 2. So a1 equals 2. Then the same process of a2. We time xs with s plus 2. We get the result as s plus 3 over s plus 1. And we are going to replace all the s with -2. So -2 plus 3 over -2 plus 1. It is -1. So here a1 is 2, a2 is -1. So the xt is 2 exponential minus t. That's the Laplace transform, inverse Laplace transform of the first element. And then minus exponential minus 2t is the inverse Laplace transform of the second term, of the second element. So you can see here, we do not need to work the xt out according to the definition to do the integration. We just do some algebraic calculation. The calculation is an algebraic calculation. It's easier than those integration calculation, right? Okay, this is a xt. Okay, xt. Right, I'll give you another example. Well, for this example, the two poles are all real numbers, are all real values. Now we show you another example. Here we have a complex one. Well, this time the x's will have the same numerator, but the denominator a little bit different. It was 3 before. It was 3 for the previous example, but here it is 2. So the roots for the denominator are no longer real ones. They are complex numbers now. They are a pair of conjugate complex number. So actually it is -1 plus minus j. That's the roots. That are the poles. So with the two poles, we can see that they are different from each other. So we can rewrite this equation into this form. So for the denominator, we separate it into two basic sections, into two basic first order polynomial. And we also do the same. It is a sum of the two basic elements with a1 and a2 to be determined. Now again, we can do the calculation in the same way. We times xs with the first polynomial, and we substitute the s with the first root. We get a1. It is a complex number. 1/2 plus j. That's the first one. And a2, the same way. The calculation is just a little bit complicated because here it is a calculation of a complex number, not just real numbers. If it is real number, the calculation will be easier. But for complex numbers, the calculation is a little bit more confusing. But doesn't really matter, because to do the calculation correctly, accurately, is a basic requirement for engineers, right? Well, I know all the Chinese people are quite good at calculations, but your foreign students, your foreign people are not good at this. We have two different education systems. We have quite a different requirement for each stage of your education. So in China, we require quite hard on these calculations, and I think it will do you good if you try to practice some more calculation to do it quickly, readily. It's helpful. Okay, right. So A1 and A2 has have been worked out. So then we can also use this. So A1 a exponential -1 minus gt plus A2 exponential -1 plus gt. And then we use Euler formula. We use Euler formula. We get this result. And by doing the calculations, well, just some complex complex calculations, we get this result that is exponential t cosine t plus 2 exponential t minus, no, 2 exponential minus t sine t. That's the xt, right? Well, that's the inverse Laplace transform. So, right. So, solving by the inverse Laplace transform, actually we have developed a way to solve linear differential equations. Well, in university, when we learn some theory for differential equations, right? When we have differential equations, we directly solve this differential equation to get the solutions. But here we have another choice. We can do the Laplace transform for the equation, and we get a imagined function. And the imagined functions are all just algebraic equations. And we solve the algebraic equations. We get imagined function. And by inverse Laplace transform, we get the solution of these differential equations. So it provides us a new way to solve the differential equations by Laplace transform. Okay. Right. Here I'll give you example. Well, here we have a differential equations x dot t equals minus 3xt plus ut. And the initial condition of x0 is 1. That is x at t equals 0. It is 1. For u, if t is smaller than 0, it is 0. If t is greater than 0, then u is unit 1. So actually u is just the unit step function we have introduced in last section an hour ago at the beginning of this class. Okay. So how do we solve the solution of xt? We try a new way. We do the Laplace transform. Well, for the left-hand side, it's the derivative of xt. So it is sxs minus x0. That's for the left-hand side, for the x dot t, the derivative of xt. For the right-hand side, it is minus 3xs plus us. Well, it is minus x 3xs plus 1 over s. 1 over s is the Laplace transform of ut, of the unit step function. Well, I have told you just now, this pair is important, very frequently used. Okay, very frequently used. So you should bear in your mind. Okay. So here we move the x0 to the right-hand side and move the minus 3xs to the left-hand side. So we put all the xs on the left-hand side, the rest on the right-hand side. We get s plus 3xs equals x0 plus xs 1 over s. And as x0 is 1, we divide each side by s plus 3. We get xs equals s1 over s plus 3. Well, here actually is x0 over s plus 3, this part. And the second part is 1 over s plus 3. Well, it was 1 over s, but now divided by s plus 3 is 1 over s plus 1 over s times s plus 3. So that's the xs. That's the xs. Then we are going to divide the xs into those basic elements. So what are those basic elements? The first one has already been a basic element, right? The first order one. And the second part is the second order one. It's not the basic ones. So we are going to divide this part into those basic parts. And this part is going to be, can be divided into two. The first one is 1/3 over s, and is minus 1/3 over s plus 3. Well, here it is just a1 over s, a2 over s plus 3. How to calculate a1 and a2? We will not repeat it again. Okay. Okay. So we have a s plus 3, 1 over s plus 3 here, and another s plus 3 here. We combine the two. So finally, we have the result that is 1/3 of 1 over s and 2/3 of 1 over s plus 3. That's the final xs. Has been divided into two basic elements. Then, with the inverse Laplace transform of these basic elements, we can get xt. So xt equals 1/3 plus 2/3 exponential minus 3t. So you can see here, traditionally, we directly do the solve the ordinary differential equation. That's the traditional way. But now we use a different way. We use Laplace transform for the original ordinary differential equation. We solve out the imaginary function of xt. Then we do the inverse Laplace transform to find out the time domain function of xt. During the process, all the calculations are just algebraic calculations. So the calculation, the process is easier. Well, this is just a simple equation. The benefit is not that big. It's not that obvious. But if you have a complicated one, this process is going to be simplified quite big, quite significantly. Okay. All right. I will give you a exercise here. It's a second order differential equation, and for the initial condition of just the same, x0 is just 1, and for the u will be just the same, it is a unit step function. I'm going to ask you to solve this ordinary differential equation now in class. So take out your piece of paper, take out your pen, and do the calculation. All right. Those who finished the calculation can write on this plan. You can use the note function. Right? You can use the note function to write it here. I will write. Right? Yes. So you can write it too. All right. Well, does any one of you finish the calculations? All right. We have just 5 minutes left. Um, I don't want to go to some other teaching contents because this part is quite a lot of the mathematics, a lot of derivations, a lot of calculations. I will leave the left 5 minutes to you to finish this exercise, and after class, you may find some examples to do the calculation, do the derivation by yourself, okay, and to read these documents to get familiar with the Laplace transform about the pairs of primitive functions and the emerging functions, okay? And if you
Okay,
find
Lord.
difficult to work this out, you may let me know in the WeChat group, okay?
Okay,
Then I
Lord.
can,
We will let you know.
yes?
Okay, Lord. We will let you know, Lord.
Right, okay.
If you face
And
any.
if you find it difficult, let me know and I will give you the details of solving this equation. I will write it by hand, okay? And I will paste it if you need that, all right? I will just
Okay,
ask
Lord.
you to, well, I will just ask you to try to work it out by yourself. Then you can paste your result in the WeChat group, all right?
Okay, Lord.
Okay. Well, we have now we have well 9 of you. So actually it's 5 now, nearly 5 in Africa, right? Nigeria, right? Nigeria, Nigeria, right?
Yes, Lord.
It's really difficult.
Yes, Lordship.
Um, but sometimes this is just what life is. When I was in Britain, I went there for 1 year from 2011 to 2012. I stayed there for 1 year. At that time, because I had quite a lot of things to deal with, a lot of domestic things to deal with. So it was 8 years time difference. When the Chinese daytime, it was midnight there, and I had to work at midnight, well, many times. And I lived in with a landlord. I rent a room from a landlord there. Um, I have to turn off all the lights, because if I keep the lights on, the light will go through the window above my door, and this will make them not sleep well. So I had to turn off all the lights. Just the screen is bright, and the brightness has to be lowered down. So my sight went down significantly for that year. Got very tired, and well, since that time, my eyesight just could not recover. So nowadays, when I watch the screen and I lift my eyes to a distant thing, it takes time to focus. I'm just well, this is the life, right? Sometimes we have to overcome some difficulties. If someone else can help, this will make it easier. But if they can't, then we have to overcome it by ourselves.
Yes, Lord.
All right.
Yes, Lordship.
Yes, Lord. We will try our best to solve it.
Yeah, but I still hope that we can find some other time, which is more, well, not that difficult for you. I hope so. Right. So my time is up. Then that's all for today's class. And the next will be on Wednesday. Next class will be on Wednesday. So if you can get agreed on the adjustment of the time, just let me know. Better a day in advance so I can talk with the secretary. All right.
All
Okay,
right,
Laushi.
all right, Laushi.
Okay, so I will see you, and I wish you a happy weekend.
Same to you.
Thank you, Laushi. Thank you so much
Okay.
for your time, Laushi.
Thank you.
Okay. So bye bye.
Bye,
Thank you.
Laushi.
Bye, Losh.